Dear students, myself I am Mamta Devi AB, Assistant Professor of Chemistry. In this video, I am going to explain sessions 52 and 53 of Radiation Chemistry. The contents of this video are definition of radiation chemistry and stages involved in radiochemical reactions, ionic yield and energy yield, comparison of radiation chemistry with photochemistry, units of radiation, that is rad, Gray and Rontgen, dosimeter, Frick dosimeter. Radiation chemistry. It is a branch of chemistry which involves the study of interaction of matter or chemical substance with high energy radiations like gamma radiations, X-rays, electron beam, etc. Radiochemical reactions. Radiochemical reactions are those reactions in which interaction of matter with high energy radiations like gamma radiations, X-rays, electron beam, etc. takes place. Radiolysis. The process of dissociation of molecules by nuclear radiations is called radiolysis. Different stages involved in radiochemical reactions. There are two stages, primary stage and secondary stage. Primary stage. This substance A is exposed to high energy radiation like gamma radiations resulting in the ionization to yield A plus ions and electrons. The pair of ion and electron formed is called ion pair. Secondary stage. In this stage, ions and electrons undergoes varieties of reactions. Some of them are as follows. The ions pair formed in the above step gives an excited molecule. Second step, an excited molecule captures a released electron to form anion of the molecule. Third step, the interaction of anion of the molecule with cation to form an excited molecule. Fourth one, the decomposition of an excited molecule into formation of either free radicals or stable molecules. Ionic yield or ion pair yield. It is defined as the ratio of number of molecules undergoing change to the ion pair formed in the given time, or it is also defined as the number of molecules that undergo change per ion pair formed in the same time. Energy yield or G value. It is defined as the ratio of number of product molecules formed per 100 eV of energy absorbed, or it is also defined as the number of molecules undergoing change per 100 eV of energy absorbed. Comparison of radiation chemistry with photochemistry. The range of wavelength used is less than 200 angstrom units in radiation chemistry, whereas in photochemistry it is between 2000 to 8000 angstrom units. In the case of radiation chemistry, energy involved is high, that is greater than 100 dV, and gamma rays, X-rays, alpha particles, electron beams are used. Whereas in photochemistry, energy involved is low, that is 1.2 to 12 electron volts. Visible, UV, near IR radiations are used. In radiation chemistry, radiation may or may not be monochromatic, whereas in photochemistry, radiation must be monochromatic. Ionic yield is calculated in radiation chemistry, whereas quantum yield is calculated in photochemistry. Reaction initiated by high energy radiations like gamma radiations in radiation chemistry, whereas reaction is initiated by energy radiations like UV and visible in photochemistry. In radiation chemistry, the primary step is ionization, whereas in photochemistry, the primary step is excitation. In radiation chemistry, effects are more drastic and complicated, whereas in photochemistry, effects are simple. In radiation chemistry, all the species, that is solute, solvent, impurities undergo change, whereas in photochemistry, in solutions, only the dissolved substance undergo change. In radiation chemistry, chemical dosimeters are used to measure absorbed energy, whereas in photochemistry, chemical actinometers are used to measure the absorbed energy. Units of radiation. The different units are available to denote the dose. that is the amount of energy absorbed by unit mass of a substance. Those units are rad, Gray and Rontgen. Rad, radiation absorbed dose. It is defined as the absorption of 100 ergs of energy per gram of the substance. 1 rad is equal to 10 to the power of minus 5 joules per gram, that is equal to absorption of 6.24 into 10 to the power of 13 EV per gram, or 1 rad is equal to 0.01 joule per kg. Gray. Gray is defined as the absorption of 1 joule of energy in the form of ionizing radiation per kg of matter. It is the SI unit of radiation absorbed. 1 Gray is equal to 1 joule per kg. 1 Gray is equal to 100 rad. Rontgen. Rontgen is defined as the amount of radiation when exposed to 1 centimeter cube of dry air at STP, which produces ions carrying 1 ESU of either sign. It is based on the ability of radiation to ionize air, or it is a measure of ionization of the molecules in a mass of air. So, 1 Rontgen is equal to 2.58 into 10 to the power of minus 4 coulombs per kg, or 1 R is equal to 0.87 rad, that is equal to 8.7 into 10 to the power of minus 3 Gray, that is equal to 8.7 milligray. Dosimeter. Dosimeter is a device or instrument used to measure absorbed dose of ionizing radiation. Dosimetry. The technique used to measure absorbed dose of ionizing radiation, or measurement of dosage used for irradiation and calculation of yield of the products formed is called dosimetry. Example, Frick dosimeter. Frick dosimeter or ferrous sulfate dosimeter. Principle. The quantity of energy absorbed induces a definite amount of chemical change, which can be measured by chemical dosimetry. It is independent of both the dose rate and nature of the radiation. Frick dosimeter is based on the study of extent of oxidation of ferrous to ferric ions induced by dose absorbed. Function of dosimeter. Dosimeter solution is prepared by dissolving 0.4 gram of more salt, 0.606 gram of sodium chloride and 22 centimeter cube of concentrated sulfuric acid in a dm cube of distilled water. A portion of this solution is exposed to gamma radiation for a certain period of time. Fe2 plus is oxidized to Fe3 plus ions. The rate at which Fe2 plus gets oxidized to Fe3 plus ions can be easily followed. If a relation between rate of oxidation and radiation absorbed is known, then the amount of radiation absorbed can be calculated. The concentration of Fe3 plus ions produced, that is X, is determined spectrophotometrically at 304 nanometer by plotting concentration of Fe3 plus against optical density. The standard yield of Fe3 plus ions is 15.5 ions per 100 dB of energy. By comparing with the standard value, the unknown dose is estimated. The sodium chloride is added to reduce or eliminate any sensitivity to organic impurities. If 15.5 Fe3 plus ions are produced by 100 dB of radiation, therefore X Fe3 plus ions are produced by 100 into X divided by 15.5 radiation. In this way, the amount of absorbed dose is measured. However, this dosimeter is used to measure low doses only. If you want to study more about these topics, refer Essentials of Nuclear Chemistry by H.J. Arnikar, Principles of Physical Chemistry by Puri, Sharma and Patania, Essentials of Radiation Chemistry by A. Majumdar. Thank you.